So in today's lesson, we will be doing waves. What are waves? So waves allow us to, so we have two types of waves. We have let me write it down in text. We have transverse and we have longitudinal. Longitudinal. Yep. So with longitudinal, it's measured in the gaps. So let me redo that. That's horrible. So you'll have less dense lines and then more dense and then back to being less dense and then back to being more dense, right? And let me just make a couple more. Right, and by the way, these lines don't have to be separate height. They are all the same height. Pretend they're all the same height. I'm not very good at drawing with this. Next we have transverse. Right, and since this is supposed to be more like a recap, I'm gonna go over this quickly. Amplitude is measured from your center line. This is amplitude. Wavelength is measured from, this is supposed to be like the same like height. It's not supposed to like not line up. It's supposed to, this one's supposed to be like shorter like that. Um, right? And yeah, we just measure it from one point to the next point, right? And we can do this for our C crests, and this is going to be T for troughs, right? Crest, from one crest to the next, or from one trough to the next trough. When you measure them from the center line, right? Don't stop here. Don't stop here. This is wrong. That's not one wavelength. One wavelength would be here, and this would all be one wavelength measured in lambda. These are all the same. Right? They're all the same. Um don't worry about where you measure them as long as you're measuring them properly. You can even measure weirdly if you measure from here and you go across, and that would still be one lambda because it's starting and ending the same, and you still have to worry about the intersections though, right? So you can still measure it like so, and that's one lambda, same as all of them. So we have lambda, we have amplitude, and then we have the speed of the wave. You can't really see the speed of the wave in the either, um, but that's fine because the speed will be in meters a second. So let's go look at our wave formula. Let's take this one. T is equal to lambda over v. T is equal to lambda over v. Right, this is what it's trying to say, is that the time interval from one point to the next point, from one like wavelength to the next, is equal to the amount, is equal to lambda over v, right? And this is one of our fundamental formulas, and we're going to be like continuously rearranging them. And here is, I have a, yeah, here's a good, this is like arranging it into a triangle, and this makes it easier. So that you know, like v over f is equal to lambda, v over lambda is equal to f, and in this case here, uh, right, this is one of our fundamental formulas. So it's going to be very useful, as well as we have another one where t is equal to 1 over f, right? So I should explain that frequency is equal to the lambda over t, right? As we know from this one, lambda over t will give you your frequency, and it basically is measured in hertz. hertz. This is the units for it, HRZ, although its full is hertz. Although you don't need to know that, you just need to know the unit is hertz, like HRZ. And it tells us the amount of wavelengths that pass through any given um, that pass through a point in 1 second. So 60 hertz means 60 wavelengths will pass by 1 second. 60 hertz is very common. You might hear it a lot, mainly because that's what your power grid is set to in most countries. So what? So we never got to what? Where do we see these transverse waves? Transverse waves are mainly seen in the EM spectrum. The EM spectrum covers a lot of things. So main thing is visible light. I'm sure you've all heard of visible light. That's what you see with. Um, Here we have it so that the wavelengths are measured in nanometers, because it just makes it easier. We don't need standard form, and frequency is measured here. So as we can see, as the frequency goes up, we can see that our wavelength actually drops, and this is because, this is inverse, right? This is inverse. So that just means that as we increase our frequency, our wavelength will drop. If you're doing 60 hertz, that means you're doing 60 wavelengths will pass in a second, right? So the wavelength needs to be physically shorter to pass through to have so many of them pass through as compared to 1 hertz, right? And that's why we see it like this. Um, so yeah, red is a lower frequency than what do you call violet, and once we get higher than violet, we call it ultraviolet, and when we get lower to red, we get infrared. That's a good way of remembering where infrared and where ultraviolet go. I remember when I was learning this, I always used to jumble them up on which one goes on which side. So that's a nice way of remembering it. We also have gamma rays, which are extremely high frequency, low wavelength, and we have radio, which is it's a super long uh, wavelength. It'll be like that, and this will be your gamma rays, right? And they would still have the same center point, um, right? The amount of amplitude in one of these waves will basically tell you the amount of energy they have. Other factors also affect the what do you call is the energy, but main thing is the amplitude. So you will be asked to remember these for your school examination because you need to remember the electromagnetic spectrum. You don't need to remember the exact numbers, just the orders. So you need to go radio, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. That's all you need to remember. And then you also need to remember the formula, but those might be included in your formula booklet. Um, so another thing with transverse waves, since it covers the EM and visible, well, I don't think I need to write down visible because you already saw that visible is part of the EM, right? These do not need mediums, right? They're a form of radiation, which means that they're carried out by electrons and photons, which means that they don't need, say, atmosphere to pass through, while longitudinal, on the other hand, is sound. So let's move on to here. So how do we still have these units, we still have to worry about them, so how do we measure them? So you can kind of think about all these when the lines are close to each other, you can think about that as a crest, and when they get really far apart, they go trump. So right? So let's see how we measure this. How do we measure one wavelength from here? We go crest, trump, crest, and that's one wavelength. So crest, trump, then back to crest. Therefore, this is one wavelength, and the frequency will be similar. And velocity is dependent on the speed of sound. So you don't need to remember any formula to calculate the speed of sound, all you need to know is that in atmosphere it's constant. As you get higher and higher up, the speed of sound actually drops, right? That's because what this is really showing is how particles are arranged. So when sound, what it really does is it takes the air molecules and starts vibrating them, and their vibration, it's seen. So if we zoomed into this, what would basically be is that you'd have your compression zone, right? These don't have to be in a grid, but I just ended up drawing them similar to a grid, right? So this would be your crest, and then, they get spaced out, and this would be your trump, right? Right? So your crest and then your trump, right? And that's the whole point. The spacing of the air molecules will give you your is what actually creates the sound. And then you have your eardrum here, and it will basically vibrate, right, left and right, and that's how you measure. That's how you hear sounds. The movement of the air molecules would be transferred over to your ear. So um, if you think about how this happens, right, you can think that if there's a lot of air in between you, the sound, the thing that creates the sound, and your ears which receive it, if the distance is high, that means the energy is going to be lost because of the space in between. So from that, we can know that energy will be lost. And generally, when the particles are closer together, the transfer of energy is going to be way more efficient. So in something like water, where all the what do you call water is all together, it better transfers the energy, which is great because if in water, you might be able to hear for further, although it's all distorted and messed up because our ears aren't used to it. Well, our ears aren't adapted to listening to sound in water, but sonar has a lot more range than normal speakers and microphones, and this is because sonar can just go for a long time. So the way sonar works is that if you think that this is your water line, right, and you have a boat, right, it's going to launch some waves. It's gonna hit, and it's going to bounce back at every single point it touches, right? So point would be there, one would be there, so it would be like a big cluster like this. When it comes back to the ship, they can then measure. Well, they know the speed of sound in water, so they'd go, okay, if it took 10 seconds and this was our speed, then we know that the distance has to be this much. And remember, the time will be double, so you have to half the time when you do this calculation because it'll be measured from there. So that about sums up waves for you. Please make sure to remember your formulas. Frequency is measured in hertz while time is measured in seconds. So 60 hertz. So 60 hertz would be that. Um, you would have one wave every 0.01 seconds, right? So if you had one wave every 0.016 seconds, and then you did that 60 times, you'd get 1 second. So therefore, 60 waves will pass through in 1 second if the time in between each in wave will be this much. You can kind of think about it like that. Um, yeah, that will be all.